In this chapter, we move from writing good instructions to building the right context around a query. That leads us to two major patterns: retrieval-augmented generation and agents. A model performs best when it has both a clear task and the information needed to complete it. When context is missing, it is much more likely to guess, and that is where mistakes and hallucinations begin. The two main ways to build context are RAG and agents. RAG pulls relevant information from external sources, while agents can call tools like search or news APIs to gather fresh information. RAG is mostly about giving the model better context. Agents go further. They let the model act through tools, work around limitations, and directly interact with the world. These patterns are exciting because they add new abilities to already strong models. Next, we'll break down how each one works and why they have become such important ideas in modern AI. Let's start with RAG, a pattern for helping models answer with the right information. The key idea is simple: retrieve relevant context first, then generate the response. RAG improves a model's output by pulling in useful information from an external source before the answer is written. That source might be a database, prior chat history, or the web. This pattern was introduced early in open domain QA. Find the most relevant documents, then let the model read them and answer from that evidence. The important shift is that the model is no longer relying only on what it already remembers. Notice the pipeline in the diagram. A query goes in, relevant documents come back, and those documents become the input for generation. That handoff from retrieval to reading is the core idea behind RAG. This figure shows the original retrieve then generate setup. The model was often described as a document reader because its job was to read the retrieved text and produce the answer. The term RAG came later, but it names the same basic strategy: bring in only the most relevant knowledge for the task. That usually helps the model answer with more detail and fewer hallucinations. If a user asks about a specific product, the model answers much better when it can see that product specifications. Without that context, it has to guess. With it, it can respond precisely. Think of RAG as building a custom context window for each question. That's especially useful when different users should only see different slices of the data. A useful analogy is classical machine learning. Feature engineering supplies the information a model needs to make sense of the input. RAG does the same thing for foundation models by constructing the right context. Even as context windows grow, RAG remains important. Many applications need more data than can fit in context, and available information keeps growing faster than window sizes do. A larger context window does not guarantee better use of that context. RAG can lower token cost, reduce latency, and focus the model on the most relevant material for the query. The broader trend is not just longer context, but smarter context use. It would not be surprising to see model systems borrow retrieval-like mechanisms to highlight the most salient parts of what they receive. There's an important practical boundary here. Sometimes the knowledge base is small enough that you can simply include it all, and RAG may not be necessary. For some models, a compact knowledge base can fit directly in the prompt, which removes the need for retrieval. The real decision is not RAG versus no RAG in the abstract, but which approach is best for the size of your data and the model you are using. In this section, we'll build the core picture of Retrieval-Augmented Generation, or RAG. First, we'll separate the retriever from the generator. Then we'll look at how documents are indexed, queried, and combined into a final prompt. A RAG system has two jobs: find useful external information, then use that information to produce an answer. The key idea is that the model is not relying only on its internal memory. It is grounded by retrieved evidence. Notice the two-stage flow here. The retriever pulls relevant chunks from the knowledge source, and the generator uses those chunks plus the user query to produce the final response. This figure summarizes the whole pipeline in one view. Keep this structure in mind, because everything that follows in the chapter will refine one part of it. The original RAG work trained retrieval and generation together, but many modern systems use pre-trained components separately. End-to-end fine-tuning can still help, because the two parts learn to work together more effectively. The retriever is the part that makes RAG work well. It first indexes the data into a form that can be searched efficiently, and then it answers queries by returning the most relevant items. In practice, the external memory may contain very long documents, so we usually split them into chunks before retrieval. After selecting the best chunks, some light post-processing combines them with a user prompt, and that final prompt goes into the generative model. There is one terminology choice to keep in mind for this chapter. The book uses the word document to mean both a full document and a chunk, which keeps the language aligned with classical IR and NLP usage. So when you see the word document here, read it broadly. In this chapter, a chunk is treated as a kind of document, which helps keep the terminology consistent with the literature. In this section, we'll look at how retrieval works in practice. The main idea is simple. Given a query, rank documents by relevance, then return the best matches. Retrieval did not begin with RAG. It's a long-standing field that powers search engines, recommendations, and log analysis. We'll only cover the key ideas here, since the full topic is much broader. One useful distinction is that retrieval usually means searching within one system or database, while search can span multiple systems. In this chapter, though, we'll use the two terms interchangeably. So if you see either word here, treat them as referring to the same basic process. The important part is that we are looking for relevant items from a collection of stored information. At the core, retrieval assigns a relevant score to each document for a given query, then sorts by that score. The algorithms differ in how they compute relevance, and we'll start with term-based methods and then move to embedding-based methods. In this section, we'll compare two major retrieval styles, sparse and dense. The key difference is whether the system matches documents by terms or by learned vector representations. You may see retrieval described as sparse versus dense in the literature. This book uses a slightly different lens, term-based versus embedding-based retrieval, which is often easier to interpret. Sparse retrievers use sparse vectors, where most entries are zero. In term-based retrieval, each term is often encoded as a one-hot vector, So only one position is active, and that position identifies the term in the vocabulary. This tiny vocabulary shows the idea clearly. Each word maps to a vector with a single one in its own slot. The vector length matches the vocabulary size, and the active index tells you which term it is. Dense retrievers use dense vectors, where most values are non-zero. Embeddings usually fall into this category, though there are exceptions like splayed, which produces sparse embeddings by pushing many values toward zero. That's why sparse versus dense can be misleading. Splayed is technically sparse. It behaves much more like embedding-based retrieval than classic keyword matching. A term-based versus embedding-based split avoids that confusion. Let's start with term-based retrieval. This is the classic keyword-driven approach, and it helps build intuition before we compare it with semantic retrieval. The simplest retrieval strategy is lexical matching. If the query contains a phrase, retrieve documents that contain the same phrase. It's straightforward, but it can struggle when the exact wording is too broad or too literal. First, many documents may match the same term, so you still need a way to choose among them. That leads to ranking signals instead of a pure yes or no match. A common heuristic is term frequency. If a term appears many times in a document, that document may be more relevant. It's a simple signal, but by itself, it can overvalue long or repetitive documents. The second issue is that not all words are equally informative. Common words should matter less than specific ones, so we need a notion of term importance. In a long prompt, some words carry much more meaning than others. Words like Vietnamese and recipes are far more useful than filler words like for or at, so retrieval needs a way to rank term importance. That idea becomes inverse document frequency, or IDF. If a term appears in many documents, it is less informative. If it appears in only a few, it gets a higher weight. In practice, IDF rewards rarity. TF-IDF combines both signals, how often a term appears in the document, and how rare that term is across the corpus. The goal is to score documents that repeatedly mention important query terms. Now we'll unpack the pieces of that formula one at a time, so the notation is easier to read. Here, the query is broken into its individual terms. That lets the scorer evaluate how each query term contributes to the final document score. Next comes the document side term count, which is the basic frequency signal used by the scorer. The term frequency of term T in document D is just F of T in D. This is the raw count of how often that term appears in that document. Then we bring in the corpus-wide rarity term, which tells us how broadly distributed the word is. IDF compares the total number of documents to the number that contain the term. A rarer term gets a larger IDF value, so it contributes more to the score. With those pieces in place, the final TF-IDF score is just a sum over the query terms. This score adds up the weighted contribution of each query term. Documents score higher when they contain more of the query's important terms, especially the rarer ones. Real systems need an efficient way to support this lookup, and that's where an inverted index comes in. Instead of mapping documents to terms, it maps terms to the documents that contain them, which makes retrieval much faster. This table shows the structure of an inverted index. For each term, you store which documents contain it, how many there are, and often extra statistics like term frequency. BM25 is a widely used refinement of TF-IDF. One important improvement is that it normalizes for document length, because longer documents naturally tend to contain more term occurrences. BM25 and its variants are still standard baselines in industry. Even modern retrieval systems are often compared against them, because they remain fast, reliable, and surprisingly competitive. A hidden but important step is tokenization, breaking text into terms. Simple word splitting can damage meaning for phrases like hot dog, so many systems also support common engrams. Retrieval systems often normalize text by lowercasing, removing punctuation, and dropping stop words. Libraries like NLTK, SpaceC, and CoreNLP provide these tools out of the box. You can also retrieve by engram overlap, but that works best when queries and documents are similar in length. if documents are much longer. Many of them will overlap by chance, and ranking becomes less discriminative. Now let's switch to semantic retrieval. The big shift here is that the system tries to match meaning, not just shared words. Term-based retrieval works at the lexical level, so it can miss intent. Embedding-based retrievers rank documents by semantic similarity, which helps when the query wording is ambiguous or when different words express the same idea. In this setup, indexing does more than store text chunks. It converts them into embeddings. Those embeddings are stored in a vector database, and at query time, the same embedding model is used on the query. The first step is to embed the query itself. That gives the retriever a vector representation of a user's intent. The query must go through the same embedding model used during indexing. That consistency is important. Otherwise, the query vector and document vectors would not live in the same space. The second step is retrieval from the vector store. Now the system looks for the closest stored vectors. The retriever returns the k-data chunks closest to the query embedding. The right value of k depends on the application because it controls both recall and how much context you pass downstream. This diagram summarizes the flow. A query is embedded, then compared against stored vectors, and the closest chunks are returned. Notice that indexing and querying are separate stages, but they use the same embedding space. This figure is the high-level view of semantic retrieval. The important idea is not the exact machinery, but the two-stage pattern. Embed first, then search nearest vectors. The workflow here is simplified. In production, systems often add a re-ranker to reorder candidates and caches to reduce latency, especially when the same or similar queries repeat. Embedding-based retrieval depends heavily on the embedding model. If the embeddings do not preserve meaningful similarity, the retriever cannot recover that later. A vector database stores vectors, but the real challenge is searching them efficiently. Given a query embedding, it must quickly find nearby vectors without comparing against everything from scratch. Vector search is not limited to RAG. It's used anywhere embeddings help organize similarity, including search, recommendations, clustering, fraud detection, and more. A common framing is nearest neighbor search. Find the k closest vectors to the query. The naive solution is exact KNN, which is conceptually simple but expensive. First, the algorithm scores the query against every stored vector. That gives you exact similarity values, but it does not scale well. Each database vector is compared with the query embedding using a similarity metric, such as cosine similarity. This is accurate, but it becomes slow as the database grows. Next, the algorithm sorts the vectors by score, so the best matches rise to the top. Once all scores are computed, the vectors are ranked from most similar to least similar. This gives the exact nearest neighbors, but only after an exhaustive pass. Finally, only the top k results are returned to the application. The output is the k highest scoring vectors. That is precise, but for large datasets the cost of getting there is too high for production use. So exact KNN is great for small datasets or for understanding the logic, but it is too slow for large-scale retrieval. That's why practical systems use approximate methods. For large datasets, vector search usually relies on approximate nearest neighbor, or ANN, methods. Libraries like FAISS, SCNN, Annoy, and HenSlib provide efficient implementations of these ideas. Most application developers won't implement these algorithms from scratch. A quick overview is still useful, though, because it helps you evaluate trade-offs in different vector search systems. ANN systems often organize vectors into buckets, trees, or graphs to make similar vectors easier to find. They may also quantize vectors or make them sparse to reduce cost. Locality-sensitive hashing groups similar vectors into the same buckets. It trades some accuracy for speed and is useful beyond vector search as well. The basic idea is to hash nearby vectors together so you can search fewer candidates. That makes lookup faster, though you may miss some exact neighbors. HNSW is a graph-based method. It connects vectors with edges to similar vectors, then navigates the graph to find nearby neighbors quickly. HNSW builds a multi-layer graph where each node is a vector. Searches move through the graph toward likely neighbors, which gives fast and accurate retrieval in practice. Product quantization compresses vectors into smaller subvector representations. That reduces the cost of distance calculations while keeping the search usable at scale. Instead of comparing full vectors, the algorithm compares compact representations. That makes search faster and is one reason Face scales so well. Inverted File Index, or IVF, uses clustering to group similar vectors together. At query time, it only searches the most promising clusters instead of the full database. IVF uses k-means to form clusters of similar vectors. Then it searches nearby centroids first, which narrows the candidate set before more detailed scoring. Annoy is a tree-based ANN method. It builds multiple random binary trees so that searches can quickly narrow down the likely neighbors. The trees split vectors using random boundaries, and search walks those trees to collect candidates. It's simple, practical, and widely used. There are several other useful ANN systems as well, including SBTAG and FLAN. The main point is that many different data structures can support approximate search. Even though vector databases became prominent with RAG, the broader idea is simply any database that can store vectors and support vector search. Many traditional databases are adding that support now. Now let's compare the two families directly. The right choice depends on speed, flexibility, cost, and how much semantic understanding you need. Both term-based and embedding-based retrieval have mature tooling, so starting either one is relatively easy. The trade-off is not whether they work, but what they optimize for. Term-based retrieval is usually faster both at indexing time and at query time. Matching terms to documents is cheaper than generating embeddings and doing nearest neighbor search. It also works well with minimal tuning. But that simplicity means there are fewer knobs to turn if you need to improve quality later. Embedding-based retrieval can often be improved by fine-tuning the model or retriever, which gives it more room to outperform term-based methods. The downside is that embeddings can hide exact keywords like error codes or product names. To judge a retriever, you need metrics that measure the quality of the return context. Two useful ones are context precision and context recall. Context precision asks, among the retrieved documents, how many are actually relevant? It is a measure of how clean your retrieved context is. High precision means you are not wasting context window space on irrelevant documents. That matters because downstream generation is sensitive to noisy context. Context recall asks the opposite question. Out of all relevant documents, how many did the retriever find? It measures whether the system is missing important evidence. High recall means the retriever is not leaving key documents behind. In RAG, recall is often crucial because missing one important chunk can hurt the final answer. To compute these metrics, you need a labeled evaluation set with test queries and relevance judgment for documents. Humans or AI judges can provide those labels, and then you score the retriever on that fixed set. In production, context precision is often easier to measure than recall. Recall requires knowing the relevance of every document, while precision only requires checking the retrieved set. If ranking quality matters, use metrics like NDCG, MAP, and MRR. These go beyond simple relevance, and check whether the best documents are appearing near the top. For semantic retrieval, the embeddings themselves should be evaluated too. Good embeddings place more similar texts closer together, and benchmarks like MTB test them across many tasks. Retriever quality also has to be judged in the full RAG system. Ultimately, retrieval is only useful if it helps produce better final answers. Whether semantic retrieval is worth it depends on cost and latency. Often the extra time for embedding generation and vector search is small compared with the full generation step, but it still affects user experience. Cost is another concern. If your corpus changes frequently, regenerating embeddings can become expensive, and vector storage or search infrastructure can add more overhead. This table summarizes the main trade-offs between the two approaches. It's a good reminder that no retriever is best in every dimension. Term-based retrieval is faster and cheaper, while embedding-based retrieval can be more semantically powerful but usually costs more. The right choice depends on your system constraints and search goals. Retrieval systems always involve a trade-off between index richness and query efficiency. More detail in the index usually means better retrieval, but slower builds and higher memory use. A detailed structure like HNSW can give high accuracy in fast queries, but is costly to build. Simpler methods like LSH are cheaper to create, but query quality is usually lower. ANN benchmarks is useful because it compares algorithms using several metrics at once. That helps you judge search quality and operational cost together, not just accuracy alone. Recall tells you how many of the true nearest neighbors the algorithm finds. Higher recall means fewer mismatches. This metric captures completeness. It matters when you care about not missing the best vectors in the database. Queries per second measures throughput. It is especially important when many users are searching at the same time. A higher QPS means the system can handle more traffic. In production, this often matters as much as raw accuracy. Build time is the cost of preparing the index. If your data changes often, this can become a major operational constraint. A fast index build is useful when the corpus is updated frequently. Slow build times can make retraining or refreshing the index expensive. Index size tells you how much storage the algorithm uses. That affects both cost and scalability. A smaller index is easier to store and maintain. That matters when you're scaling to very large corpora. BER is a benchmark suite for retrieval evaluation. It gives you a standardized way to compare systems across many common tasks. The big evaluation lesson is simple. Measure both the pieces and the final system. You want to know whether retrieval works on its own and whether it improves the overall RAG output. First, evaluate retrieval quality directly. This tells you whether the retriever is bringing back useful context before the generator ever sees it. Next, evaluate the final answer quality. Even a good retriever can fail if the final generation step is weak, so the end result still needs its own evaluation. Finally, check the embedding quality when using semantic retrieval. If your retrieval system depends on embeddings, you should verify that those embeddings are meaningful and useful for the task. In practice, the best retrievers are often combinations of simpler methods. The reason is that different algorithms have different strengths, so combining them can give you a better overall system. When you combine term-based and embedding-based retrieval, that is called hybrid search. It often gives you both lexical precision and semantic flexibility. A common pattern is to use a cheap retriever first, then re-rank the candidates with a more expensive method. This keeps the system efficient while improving final quality. For ambiguous terms like transformer, a keyword pass can narrow the candidate pool, and vector search can then choose the documents that match the intended meaning. That same pattern works for many query types. You can also run several retrievers at once and merge their rankings. This ensemble approach is useful when each retriever catches different kinds of relevant documents. Reciprocal rank fusion, or RRF, is one way to combine ranked lists. Documents that rank highly across multiple retrievers get boosted more strongly. The intuition is simple. A document that appears near the top in several lists should end up near the top overall. The full formula just makes that idea more precise. This formula adds a contribution from each ranked list. Lower ranks give higher scores, and the constant K keeps the lower ranked items from dominating the result. Here, N is simply the number of retrievers contributing rankings. More lists mean more sources of evidence for the final score. This term is the rank assigned to document D by retriever I. The better the rank, the larger its contribution to the fusion score. The constant K prevents division by zero and reduces the impact of lower-ranked documents. In practice, a value like 60 is commonly used. In this section, we'll look at practical ways to improve retrieval quality. The goal is simple. Get the most relevant information into the model's context with less noise and less waste. There are four main tactics to focus on here: chunking strategy, re-ranking, query rewriting, and contextual retrieval. Each one helps the system surface better documents for the task at hand. We'll start with chunking because how you split data affects everything downstream. Good chunking can make retrieval much more accurate, while poor chunking can hide important context. Chunking depends on how you plan to retrieve later. If you assume documents are already split well, you may miss the fact that the splitting itself can be the biggest factor in retrieval performance. The simplest approach is fixed-size chunking, by characters, words, sentences, or paragraphs. It's easy to implement, but the unit you choose changes how much meaning each chunk preserves. Recursive splitting is more context-aware. You break large sections into smaller pieces only when needed, which helps keep related information together instead of cutting it apart arbitrarily. Some content needs special handling. Code, Q&A pairs, and languages like Chinese may need custom splitters so the chunks match the structure of the document instead of forcing one generic rule. Without overlap, a chunk boundary can split an important idea in half. Overlap gives boundary text a second chance to appear in a nearby chunk, which reduces the risk of losing meaning. Chunk size also has to respect model limits. The chunk must fit inside the generator's context window, and for embedding systems, it must also stay within the embedding model's limit. You can also chunk by tokens, using the model's tokenizer as the boundary. That makes the chunks line up better with the downstream model, but switching models may force you to reindex everything. Smaller chunks let you fit more pieces into context, so the model can see a wider range of information. That can improve answer quality when the relevant evidence is spread across a document. The trade-off is that tiny chunks may drop the very information you need. If the key idea is split across chunks, retrieval may return only part of the evidence and weaken the answer. There's also a computational cost. More chunks mean more embeddings, a larger search space, and usually slower retrieval, especially in vector search systems. There isn't a single best chunk size or overlap setting. The right choice depends on your data, your model, and the kind of questions you need to answer, so experimentation is essential. Next is re-ranking. This is where you take an initial set of retrieved candidates and refine their order to better match the task. Re-ranking is useful when you need to narrow the set of documents before sending them to the model. It helps you keep the best evidence while staying within token limits. A common pattern is to use a fast retriever to gather candidates, then apply a more accurate but more expensive method to re-rank them. They give you a good balance between speed and quality. Re-ranking can also use recency. In systems where freshness matters, newer items should often outrank older ones, like in news, email, or market analysis. In search, exact rank is critical because users inspect the top results. In context re-ranking, order still matters, but the main goal is simply to place the most useful items where the model can use them well. Now, let's look at query rewriting. This helps when the user's question depends on prior conversation and is not clear on its own. Query rewriting goes by several names, but the idea is the same. Turn an underspecified request into a standalone query that retrieval can understand reliably. This conversation shows the problem clearly. The last question is incomplete by itself, so a retriever that sees only that line would miss the connection to purchases and likely return the wrong documents. To retrieve well, you rewrite the question so it includes the missing context. Here, the rewritten version becomes a full question about Emily Doe's last purchase. This is not specific to retrieval-augmented generation. Search engines do it with heuristics, and AI systems can do it with another model prompted to restate the user's intent. Notice how the rewritten query makes the user's intent explicit. The key idea is that the rewritten form can now be searched or embedded on its own without relying on the earlier turns. This figure reinforces the same workflow. One model can rewrite the question before retrieval. That extra step often makes the search input much cleaner and more precise. query rewriting can get tricky when it requires identity resolution or outside knowledge. In those cases, the system should admit uncertainty rather than inventing a name or fact. The last tactic is contextual retrieval. Here, the idea is to enrich each chunk so the retriever has more clues about what that chunk means. A simple version is to attach metadata, such as tags, keywords, titles, or descriptions. That extra context gives the retrieval system more hooks to match against the user's query. You can also extract entities automatically and store them as metadata. That way, even if the original text is embedded, the system can still retrieve it using a specific term from the chunk. Another useful trick is to attach example questions to each chunk. For support articles, this helps retrieval connect user phrasing like, "I forgot my password," to the right article. If a chunk has too little standalone meaning, you can generate a short summary that explains where it came from and what it is about. Anthropic used this kind of short context to make chunks easier to retrieve. This prompt asks a model to write a compact description of the chunk in the context of the full document. The important part is that the output is short and focused because it will be prepended to the chunk before indexing. Once the context is generated, it gets attached to the chunk and then indexed normally. That means retrieval sees a more informative version of the chunk without changing the original source text. Look at the flow here. The chunk is first augmented with context and only then indexed. That sequencing is what makes contextual retrieval work in practice. This figure summarizes the full idea. By adding a brief, document-aware context to each chunk, the retriever gets a much better chance of finding the right evidence later. In this section, we'll look at the practical questions that separate a good retrieval system from one that only looks good on paper. The goal is to evaluate how well a solution fits your data, your traffic, and your operational needs. A useful evaluation starts with a checklist. We want to understand what the system can do, how it performs, and whether it will still work as your application grows. These are the questions we'll use as our review framework. Each one points to a different risk or capability you should verify before choosing a solution. First, check what retrieval mechanisms are supported. If you need both keyword matching and semantic retrieval, hybrid search can be a major advantage. This is the next item in the checklist. We're moving from general retrieval features to the specifics of vector-based search. If you're using a vector database, you need to know which embedding models it works with and which search algorithms it supports. Those choices affect both retrieval quality and performance. Now we're asking whether the system can handle production scale, not just small demos. That includes both storage growth and request volume. Scalability means two things here: how much data the system can store and how much query traffic it can serve. You also want to know whether it matches your real traffic pattern, not just peak benchmarks. Indexing speed matters because it affects how quickly your data becomes searchable. Bulk operations matter when you need to ingest or update large batches efficiently. Ask how long indexing takes and how much data can be processed in one bulk operation. That tells you whether the system can keep up with refreshes, backfills, and large updates. Latency is the user-facing part of retrieval performance. Even a strong ranking method can fail if it responds too slowly. Measure query latency for the retrieval algorithms you actually plan to use. Different methods can have very different response times, and that directly affects application experience. Cost is especially important for managed services because the pricing model can change how you design and scale the system. For managed solutions, look closely at pricing. Some systems charge by stored documents or vectors, while others charge by query volume, and that changes the economics of the whole application. This list is not exhaustive. In enterprise settings, you would also evaluate access control, compliance, and the separation between data plane and control plane. Now we move beyond the classic text-only RAG setup. The key idea is that retrieval can pull in other kinds of external data, not just documents, and those extra sources can make answers much more grounded. Text is only one source of context. In practice, a RAG system may also need images, audio, video, or even structured tables to answer the user well. First, let's look at multimodal retrieval. Here, the model is not limited to text. It can retrieve images or other media that help answer the question. If the generator understands multiple modalities, the retriever can bring back both text and images. The example here is simple. A question about the color of a house can be answered better if the system retrieves the relevant image along with supporting text. Notice the pattern in this diagram. The query is matched against multiple sources, and the retrieved context can include both text and visual evidence. That is what makes the answer less dependent on language alone. This figure summarizes the idea. A RAG system can augment a query with more than one modality. The main point is that retrieval is no longer tied to text-only data. A simpler approach is to retrieve images through metadata like captions, titles, or tags. If that metadata matches the query, the image becomes useful context even before you inspect the pixels themselves. If you want to search by image content, you need a shared embedding space for text and images. That is why multimodal embedding models matter. They let a text query and an image be compared numerically. The retrieval workflow starts with indexing. We first prepare embeddings for every item we want to search over. At indexing time, generate embeddings for both texts and images and store them in a vector database. That way, different media types can be searched using the same similarity machinery. Next, turn the user's question into the same embedding space, so it can be compared fairly against the stored items. Given a query, generate its clip embedding. Now the question itself can be represented in the same space as the candidate texts and images. The final step is retrieval. Search for the nearest matches in that shared space. Query the vector database for items whose embeddings are close to the query embedding. Those nearest neighbors become the context the model uses to answer. Now let's switch to tables. This is a very different kind of retrieval problem because the system may need to reason over rows, columns, and aggregates rather than just documents. Many real applications combine unstructured data with structured tables. When the answer depends on table data, classic text retrieval is not enough. The system often needs SQL-based access instead. Here's a simple e-commerce example. The important thing is not the cat-themed products. It's that the answer to a user question may require querying a sales table directly. This table shows the kind of structured data the system has to work with: order IDs, products, prices, units, and totals. A question about sales can be answered by computing over these rows rather than retrieving a paragraph of text. To answer this question, the system has to filter the right rows and sum the units. That means retrieval here is really a database operation, not a document lookup. This SQL query does exactly what the question asks. It sums the units, restricts the table to Fruity Fedora, and limits the result to the last 7 days. The important part is that the query expresses the user's intent precisely enough for the database to execute it. The full workflow has 3 stages. First, generate SQL, then run it, then turn the result into a natural language answer. So the model is not just retrieving context, it is orchestrating a database operation. The process begins by deciding what query should be run against the table schema. Text-to-SQL maps the user's question and the available schema into a valid SQL query. This is a form of semantic parsing because the system is translating meaning into a structured command. After the SQL is generated, the next step is straightforward execution. Here the database actually runs the query. This step matters because the answer comes from computed table results, not from the language model inventing a response. Finally, the system uses the returned result to write the response in natural language. At the end, the model turns the SQL result back into a user-friendly answer. This last step keeps the interface conversational while grounding the answer in table data. This diagram ties the pieces together. The user asks a question, the system converts it to SQL, executes it, and then generates the final answer. The key takeaway is that structured data often requires a tool, not just a retriever. This figure shows the tabular version of RAG. It makes clear that the retrieval step may actually be a query over a database schema rather than a vector search. When there are many tables, you may not be able to fit every schema into the model context. In that case, An intermediate table selection step can help the system choose which tables matter before generating SQL. The big lesson is that retrievers and SQL executors let models handle more kinds of questions with better grounding. In the next section, we'll go one step further and see how tool use becomes central to agentic systems. In this section, we'll define what an agent is and why agents matter for modern AI. We'll also look at what gives agents their capabilities, where they can fail, and how we can evaluate them responsibly. A useful way to think about AI is as the study of rational agents, systems that choose actions to achieve goals. That framing comes from classic AI, and it still shapes how we talk about intelligent behavior today. Foundation models change the picture by making autonomous assistance much more feasible. Now we can build systems that plan, act, and coordinate work across many tasks, from research and scheduling to customer support and negotiation. Before we go further, one caution: this is still a new area. The field does not yet have fully settled theories for how to define or measure agents, so the framework here is practical rather than final. That means this section is intentionally a best effort synthesis of current ideas. It is useful, but it should be treated as a working model that will likely change as the field matures. We'll start with the basic idea of an agent, then move to two factors that strongly affect performance: tools and planning. After that, we'll look at the new kinds of failures agents can produce and how evaluation helps catch them. Even though agents feel new, they build on techniques you've already seen, like self-critique, chain of thought, and structured outputs. So this section connects those earlier ideas into a more capable system. In this section, we define what an agent is and what makes it different from a plain model. We'll focus on the two core parts: the environment it works in and the actions it can take. The word agent is used in many ways, but here we want a precise engineering definition. The key question is simple: what can the system observe, and what can it do in response? An agent is anything that can take in information from its surroundings and then act on that surroundings. So every agent is defined by its environment and by the actions available to it. The environment is determined by the task. For a game agent, it is the game world. For a scraper, it is the web. For a robot, it is the physical setting it operates in. In modern AI systems, tools enlarge the action set. A model that can search, run code, or query a database can do much more than a model that only writes text. These two pieces are tied together. The environment tells you what actions make sense, and the tools you give the agent limit where it can actually operate. This example shows a coding agent working inside a computer. Its world is the terminal and file system, and its tools are practical coding actions like searching, viewing, and editing files. Notice how the interface is centered on code and file navigation. That tells you the agent is not chatting in the abstract. It is acting inside a real software environment. This figure labels the agent as a coding system built around GPT-4. The important idea is that the model is only one part of the system. The environment and tools define what it can actually accomplish. At a high level, an AI agent takes a user task, reasons about it, uses feedback from the environment, and keeps checking whether the job is done. The planning loop is what turns a model into an agent. Now let's apply the idea to a simple RAG agent. The agent has a few actions available, and it uses them to gather evidence before making a forecast. First comes the initial step in the loop. The agent starts by deciding what it needs before it can answer the question well. Here, the agent thinks through the problem and realizes it needs historical sales data. That intermediate reasoning is useful because it determines the next action, not just the final answer. Next is the tool step that turns the plan into something executable. The agent now asks for a query that can retrieve the 5 years of sales data. This is where language understanding becomes a concrete database action. Once the query exists, the agent can actually run it. This is the execution step. The tool returns real data from the database, which the agent can then use as evidence. Now the agent evaluates whether the evidence is enough. After seeing the output, the agent may decide the data is incomplete or unreliable. If so, it asks for more context, such as marketing campaign history, before making a projection. The same loop repeats with a new information need. Now the agent prepares additional database queries for campaign data. The key point is that planning is iterative, not one and done. Then the agent runs those new queries as well. This gives the agent a broader evidence base. Each tool call is part of the same decision-making loop. With enough information collected, the agent can move to the final answer. At this point, the agent concludes that it has enough data to forecast future sales. The final output is based on the accumulated evidence from the tools. The last step is to close the loop cleanly. The agent checks that the original task has been satisfied. That completion check matters because an agent should know when to stop acting. Compared with ordinary model use, agents usually demand more capable models. The reason is that tool use introduces both more chances for error and higher consequences when something goes wrong. There are two important pressures here, and the next 2 points make them explicit. When a task has many steps, small errors multiply. Even a very accurate model can become unreliable over long action chains, because success depends on every step going right. The second issue is risk. Once an agent can take action through tools, failures can affect real systems, real data, or real users. That means agent errors are often more serious than simple answer mistakes. The tool access makes the system more powerful, but also more dangerous if it is wrong. Multi-step agents can take time and money to run, but they can also save substantial human effort. So the cost is justified when the agent can reliably do work on its own. The success of an agent depends on three things together: the environment, the tools it can use, and the strength of the planner behind it. Next, we'll look at the kinds of tools a model can use. In this section, we'll look at why tools matter for agents. A model can be useful on its own, but external tools greatly expand what it can perceive and do. An agent does not need tools to exist, but without them, its abilities are narrow. A text model mostly generates text, and an image model mostly generates images. Tools are what let an agent do much more. Tools usually do one of two things. They let the agent observe the world, or they let it change the world. We call those read-only actions and write actions, and that distinction matters for safety and design. Here we're focusing on the kinds of external tools agents can use. Later, in the planning section, we'll talk about how an agent decides when to call them. An agent's tool inventory is the set of tools it can access, and that set defines its practical abilities. More tools can help, but too many tools can also make the system harder to understand and use well. A useful way to think about tools is in three groups: tools that add knowledge, tools that extend capability, and tools that let the agent act on its environment. That framework makes it easier to choose the right tools for the job. First, let's look at tools that improve what the model knows at the moment it answers. These tools supply context, which is often the difference between a vague answer and a useful one. Retrievers, SQL executors, and similar tools let an agent pull in relevant information before it responds. That can mean private company data, internal search results, or even an email thread the model would not otherwise see. Some tools expose internal systems and private processes, while others connect the agent to public information. Both are useful, but they serve different kinds of questions. Web browsing is important because models can become outdated as training data ages. With access to current information, the agent can answer questions about news, weather, prices, events, and other fast-changing facts. Here, web browsing means more than a literal browser. It also includes search APIs, news feeds, and platform APIs such as GitHub or social media services. Fresh information helps reduce hallucinations, but internet access also introduces risk. You want to choose sources carefully so the agent is not exposed to low-quality or unsafe content. The second category is tools that help with things models are inherently weak at. These tools do not just add information. They make the model more capable in a concrete way. A calculator is the simplest example. Instead of forcing a model to learn precise arithmetic, it is much easier to let the model call a tool that already does that job reliably. Calendars, time zone converters, unit converters, and translators all remove common friction. These are small tools, but they can dramatically improve the quality of the agent's answers. Code interpreters are especially valuable because they let the model run code instead of merely talking about it. That makes the agent useful for analysis and experimentation, but it also means security has to be taken seriously. External tools can also turn a narrow model into a multimodal system. A text model can call an image generator, a charting tool, a latex renderer, or a browser to produce outputs it could not create alone. The same idea works in the other direction too. If a model only understands text, tools like captioning, transcription, and OCR let it work with images, audio, and PDFs. In practice, tool use can outperform prompting alone and even fine-tuning. The chameleon result is a good example. A model with a strong tool set can beat the base model on several benchmarks. Those benchmark gains are not small. They show that adding the right tools can materially improve performance on both science questions and structure math problems. Now we move from reading to acting. Right actions are the ones that actually change something in the environment, so they're much more powerful and much more sensitive. A tool may simply retrieve information, or it may modify data and state. That difference shows up everywhere, from databases and email systems to banking APIs. Once right actions are allowed, the agent can do real workflows from start to finish. It can research, contact, follow up, extract results, and update systems automatically. That power also creates risk. You would never give an unreliable system permission to make irreversible changes without strong controls, and the same caution applies to AI agents. The harm from an agent does not need to be physical to be serious. It can affect markets, privacy, misinformation, and other high-impact systems, so defensive design matters. These risks are real, but they're not a reason to avoid action entirely. The goal is to build enough trust and protection that useful autonomous systems can operate safely. The main takeaway is simple. Tools make models dramatically more capable. That is why function calling and broad tool support are becoming standard parts of modern AI systems. In this section, we'll look at how an agent turns a task into an executable sequence of steps. The key idea is that good planning is not just about generating actions, but about choosing actions that actually lead to the goal under the given constraints. A task is defined by what you want to achieve and what limits you have to respect. For example, a trip planning task has a destination and duration as the goal and a budget as a constraint. When a task is complex, the model needs to break it into steps. The result is a plan, a roadmap of actions that should move the agent toward the goal, ideally by comparing several possible approaches and choosing the best one. Planning is a deep research problem, not a small implementation detail. Here, we only need the surface view, enough to understand why agents need planning, validation, and execution as separate concerns. Now let's zoom in on how planning works in practice. The important question is not just whether a solution is correct, but whether it is efficient and likely to succeed. A single query can often be decomposed in multiple valid ways. Some plans are correct, but wasteful, so an agent should prefer the one that narrows the search space early and avoids unnecessary work. Here is the first strategy we might try. This approach starts with a broader set, all companies without revenue. After that, it filters by fundraising amount. It may work, but it can be expensive because the first set is very large. And here is the second strategy to compare against it. This version starts from a smaller, more selective set, companies that raised at least $1 billion. Then it checks which of those have no revenue, which is usually much more efficient. The second option is better because it reduces the number of candidates much earlier. A good planner should prefer the path that is cheaper to explore while still reaching the correct answer. You can ask a model to think through steps and execute them in one pass, but that is risky. If the plan is bad, the system may spend a long time and a lot of money carrying out work that never had a chance of succeeding. A safer design separates planning from execution. The agent first proposes a plan, then a validator checks it using rules or another model, and only validated plans are allowed to run. If the plan looks bad, generate another one. If it looks good, execute it, possibly through tool calls, and then evaluate the results again. In practice, this may happen at the level of a whole task or just a subtask. This diagram shows the core loop. Generate a plan, validate it, then execute only if it passes. Notice that the system is not trusting the first idea blindly. It is adding a check before action. This figure summarizes the same idea visually. The main takeaway is that planning and execution are intentionally separated, so the system can reject weak plans before they cost time or money. A practical system often has three roles. One component creates plans, one evaluates them, and one carries them out. If you treat each role as an agent, you get a simple multi-agent setup. To reduce latency, you can generate several candidate plans at once and let an evaluator choose among them. The trade-off is straightforward. Faster selection can cost more compute. Planning starts with understanding what the user really wants. Intent classification helps the agent decide how to decompose the task, and it can itself be implemented as another model or prompt-driven component. Once you know the intent, you can select better tools. Billing questions may need payment history, while password reset questions may need documentation retrieval. So the same agent should not use the same tool for every query. There is also a useful safety boundary here. Not every request should be handled by the agent, and the system needs a way to recognize that early. Some requests are simply out of scope. A good intent classifier should label them as irrelevant, so the agent can decline politely instead of wasting computation on an impossible answer. Automation does not have to be all or nothing. Humans can generate plans, validate them, or handle risky actions, and the system should define exactly which steps require human approval. We can now summarize the workflow. Solving a task usually means planning, checking, executing, and then checking the results again if needed. First comes the planning stage. The agent decomposes the task into manageable actions. This is the point where high-level intent becomes a concrete sequence of steps. Next comes evaluation of that plan. The plan is checked for quality. If it looks weak or invalid, the system does not commit to it. It generates a better one instead. Then the agent executes the chosen plan. Execution means carrying out the actions in the plan, often by calling functions or external tools. This is where abstract planning becomes observable behavior. Afterward, the system checks the outcome. The agent evaluates what happened and compares it to the goal. If the task is not complete or mistakes appear, it corrects course and produces a new plan. You've already seen this pattern in prompting. Asking a model to think step by step is really asking it to break the task down, and asking it to verify an answer is asking it to reflect. Now we can ask a harder question. Can foundation models truly plan? The answer is still debated, and the key issue is whether a language model can reliably search over actions and outcomes. Some researchers argue that autoregressive language models cannot really plan, only generate text that looks like plans. The concern is that a plausible-looking sequence may still fail when actually executed. At the same time, it is not settled whether the limitation is fundamental or whether we simply have not built the right prompting, tools, and control loops yet. A useful way to think about planning is as search. You explore possible paths to the goal, estimate how good each path looks, and then choose the most promising one, or conclude that no workable path exists. Search is rarely a straight line. If one action leads to a poor state, the planner has to backtrack and try an alternative path from an earlier decision point. Even if a model produces actions left to right, it can still revise an earlier choice by discarding a bad path and generating a new one. So the inability to literally backtrack token by token does not necessarily mean the model cannot plan. Planning also requires a model of what each action will do. It is not enough to know the available actions. The agent must estimate the resulting state so it can avoid dangerous or unhelpful moves. This is why simple action lists are not enough. A model may need an internal world model that predicts consequences, so the generated plan reflects both the action and its likely result. Even if an LLM is not the whole planner, it can still be a useful part of one. With search tools and state tracking around it, The model can help explore options and support better decisions. In this section, we compare two ways to build planners for agents: reinforcement learning and foundation models. The main question is where the planning ability comes from and what trade-offs each approach creates. In reinforcement learning, an agent is defined by the actions it takes in an environment and by the goal of maximizing cumulative reward over time. That definition is the baseline for understanding how RL planners work. Both kinds of agents interact with environments and action spaces, but the planner is learned differently. RL planners are trained with an RL algorithm, which can be expensive, while FM agents use the model itself as the planner and often need less compute to adapt. These categories are not mutually exclusive. A foundation model agent can also use reinforcement learning techniques, and over time the two approaches may converge into hybrid systems. Now we move from the high-level comparison to the practical problem of getting a model to produce a plan. First, we'll look at prompt engineering, then at the limits of exact function-based planning. A simple way to get planning behavior is to instruct the model directly with a prompt. The example uses a product helping agent, and the point is that the model can be guided to choose tools in a sensible order, even before any fine-tuning. This prompt turns planning into a constrained text generation task. Notice that it gives the model a fixed action set, a required output format, and a few examples. So the model learns to emit a valid sequence instead of free-form reasoning. There are two important ideas hidden in this example. One is about how we represent plans, and the other is about how the model fills in missing details from prior tool outputs. First, let's separate the structure of the plan from the meaning of each step. A list of functions is just one way to organize an agent's behavior. Different systems can use different plan formats, so the important part is the control logic, not this exact syntax. Second, the model often has to carry information from one step into the next. Here, the query generator reads the task history plus the latest tool result, then creates the next query to feed into the response stage. This is how intermediate observations become part of the agent's memory. This is a concrete planning example. The user asked for the price of the best-selling product last week. So the agent must first discover the product, then look up its details, and only then formulate the final answer. The sequence shows the overall workflow clearly. First get the date, then retrieve the top products, then inspect the chosen product, and finally generate the user-facing response. The important thing to notice is that the plan is only the skeleton. The actual arguments still need to be filled in later. The tricky part is that function arguments are not always known ahead of time. The model often has to infer them from earlier tool outputs. So the planning problem includes both choosing the next action and deciding what values to pass. This is what the next step might look like after the model sees the date. The model has to translate the date into a correct time window and choose a sensible value for how many products to retrieve. Not every request contains enough information to pin down the exact arguments. When a user leaves key values unspecified, the model has to guess, and that guess may be wrong. Let's look at the two most common sources of ambiguity. The first ambiguity is quantity. The user may not say how many best-selling products to examine. That leaves the agent to invent a default or ask a clarifying question. The second ambiguity is time range. The user may also omit the date window, and that changes the meaning of the task completely. Best-selling products last week, last month, and all time can lead to very different answers. So the agent is often forced to guess, and those guesses are a major source of planning errors. A small mistake in a parameter can make the whole plan incorrect, even if the tool choice was right. When both the action sequence and the arguments are generated by the model, hallucinations can appear in either place. The model may invent a tool that does not exist or call a real tool with the wrong values. There are several practical ways to make planning better, and most of them are familiar from general model improvement. The theme is simple: reduce ambiguity, improve guidance, and use stronger models when needed. One common lever is to give the model better examples to learn from. A stronger system prompt with more examples gives the model a clearer pattern to imitate. This often improves both the structure of the plan and the reliability of tool selection. Another lever is the quality of the tool interface itself. Clearer tool documentation also helps a lot. If the model understands what a tool does and exactly what each parameter means, it is less likely to misuse it. Sometimes the right fix is to simplify the tools. Another option is to redesign the tools themselves. If one function is too complex, splitting it into smaller functions can make planning easier for the model. And if the task is simply hard, a stronger model may help. Planning quality usually improves with model capability. If the task is hard, a stronger model may be the simplest way to reduce planning mistakes. Finally, you could train directly for the planning task. Finally, you can fine-tune a model specifically on plan generation data. That lets the model learn the structure of your tool use problem more directly. Now we switch from prompt-based planning to the API pattern most providers expose today. Function calling makes tool use more structured, and that is what turns a language model into a more reliable agent. In many APIs, a tool is just a function with a name, parameters, and documentation. The model selects the function, fills in arguments, and the application executes it on the model's behalf. The function calling workflow starts with declaring the tools you want available. The first step is to declare the tools you want available. Think of this as building the menu of possible actions before the model ever sees a user query. Each tool needs an entry point, its parameters, and a short description of what it does. Good metadata makes the model much better at choosing the right function and filling in its inputs. Next, you decide which of those tools are available for a specific query. You can also choose which declared tools are available for a particular request. That lets the application narrow the model's options to the tools that actually make sense for the current task. Some APIs go further and let you control tool behavior explicitly. That extra control is useful when you want to force tool use, forbid it, or let the model decide. These settings are common. Required means at least one tool must be used. None means no tool should be used, and auto lets the model decide. This is a simple but powerful way to steer agent behavior. This figure is shown in pseudocode, so the idea generalizes across providers. The exact syntax differs from one API to another, so you always need to consult the relevant documentation. This screenshot illustrates the API response when a model decides to call a tool. The key thing to notice is that the model returns structured arguments rather than a plain text answer. This example shows a model selecting from two tools. The lesson is that function calling can constrain the output into something your application can execute directly. Once the query is given, the agent can automatically choose the tool and fill in its parameters. Some systems can validate the function name, but they still cannot guarantee that the parameter values are correct. Here the model recognizes that it needs a pounds to kilograms conversion and extracts the number 40 as the argument. That is a good illustration of tool selection plus argument extraction in one step. This is the structured response that tells the application to call the conversion function. Notice the key parts. The finish reason signals tool use, and the argument's object contains the extracted value 40. From this response, the application can invoke the function with the extracted argument and use the result in the final reply. The model is not answering directly here. It is handing control to the tool layer first. Here is a practical habit. Always inspect the parameter values your agent proposes. That check catches a lot of silent planning errors before they reach the user. When you build or debug an agent, ask it to report the exact values it intends to pass into each function. That makes it much easier to spot mistakes in time ranges, counts, IDs, and other hidden assumptions. Next, we look at how detailed a plan should be. Planning is not one fixed level of detail. You can choose coarse, medium, or very fine-grained steps depending on the task. A roadmap can describe a task at many levels of detail. For example, a yearly plan can be broken into quarters, months, or weeks, and each level gives you a different balance of abstraction and precision. There's a trade-off here. Detailed plans are harder to create but easier to follow, while high-level plans are easier to generate but harder to execute. Hierarchical planning handles this by planning at multiple levels in sequence. If the plan names tools exactly, the plan becomes tied to a specific API. That is fragile, because a small tool rename can force you to rewrite prompts, examples, and even fine-tuning data. If the model learned the old tool inventory, it may need to be trained again after the tools change. That is one reason rigid, API-specific planning can be expensive to maintain. A common workaround is to let the model plan in natural language instead of exact function names. That makes the planner more reusable across APIs and easier for the model to generate reliably. This plan keeps the steps at a human-readable level. The idea is that a separate component can later translate each step into the exact executable function, which decouples planning from execution. Because the plan is closer to ordinary language, it is less sensitive to API changes and often easier for the model to produce. In practice, that can also reduce hallucination compared with forcing exact function syntax too early. The trade-off is that you now need a translator from natural language actions to executable commands. But that translation step is much easier than full planning, and weaker models can often handle it safely. Now we move beyond simple one-step-at-a-time plans. Real agents often need richer control flow, where different branches of the plan can run in different ways. So far, the examples have been sequential, but control flow is broader than that. Agents may need parallel execution, conditional branches, or repeated loops, depending on the task. Sequential control means one action happens after the previous one finishes. This is the simplest pattern, and it works well when later steps depend on earlier results. A good example is translation before execution. You cannot run the SQL query until the natural language request has first been turned into SQL. Dependency drives the order. Parallel control means tasks can happen at the same time. That is useful when the subtasks are independent and you want to reduce total latency. For example, if you need many product details, the agent can fetch several of them concurrently instead of one by one. That can make the user experience much faster. Conditional control flow means the next action depends on what the previous step returned. The agent first checks the evidence, then chooses the branch that best fits the outcome. A stock trading example makes this clear. Read the earnings report first, then decide whether the next step should be to buy or sell. The decision comes from the observation, not from a fixed script. Looping control flow repeats the same action until a condition is satisfied. This is useful when the agent needs to search, sample, or retry until it reaches an acceptable result. A simple example is generating random numbers until one of them is prime. The key idea is that the agent keeps going until the stopping condition is true. The next figure summarizes these control flow patterns visually. The diagram helps show that planning is not just about what to do, but also about when and how actions are allowed to run. This figure compares the major execution patterns side by side. Watch for the difference between a strict chain of steps, a branch, a repeat loop, and tasks that can run in parallel. This figure gives you a quick visual vocabulary for agent control flow. Once you can name these patterns, it becomes easier to design and evaluate real agent frameworks. In traditional software, the branching logic is exact and written by a developer. With AI agents, the model often decides the flow itself, which makes non-sequential plans harder to generate and harder to translate into code. When you evaluate an agent framework, ask whether it can run many independent tasks at once. Parallel execution can dramatically reduce the time the user feels they are waiting. The last major planning idea is reflection. Good agents do not just produce a plan once. They keep checking whether the plan is still working and adjust when it is not. Reflection is not always required for an agent to run, but it is often necessary for an agent to succeed. The point is to notice mistakes early enough to recover from them. Reflection can be inserted at different moments in the task pipeline. That flexibility is what makes it useful in practice. The first checkpoint is right after the query arrives. One opportunity is right after the user asks the question, "Can the system actually do this task?" That early check can prevent wasted effort on impossible requests. The second checkpoint comes immediately after planning. Another useful checkpoint is immediately after plan generation. At that point, the agent can ask whether the steps make sense before spending tokens on execution. The third checkpoint is during execution. Reflection can also happen after every action. That gives the system a chance to correct course as soon as it sees a bad result or an unexpected observation. And the final checkpoint is after the task is complete. The final checkpoint is after the whole plan has run. At that stage, the agent decides whether the task is truly complete or whether another round of correction is needed. Reflection and correction work together. Reflection identifies what went wrong, and correction uses that insight to improve the next attempt. In other words, reflection is the diagnostic step, and correction is the repair step. You can implement reflection with the same agent through self-critique prompts or with a separate evaluator that assigns scores. Both approaches aim to make the system judge its own progress more explicitly. React is a widely used pattern that interleaves thinking, acting, and observing. The agent explains what it is doing, takes a step, reads the result, and repeats until it is done. This template shows the rhythm of React. Think, act, observe, and continue. The final line is important because it tells the agent when to stop and return the answer instead of taking another tool action. The next figure shows React applied to a multi-hop question-answering benchmark. It is a good example of how reasoning plus tool use can solve questions that require several evidence steps. Reflection can also be distributed across multiple agents. One agent can act, while another evaluates the results and pushes the process toward a better next step. If the first attempt fails, the agent can analyze why and use that diagnosis to revise its plan. That is how agents can improve on tasks like coding, where the error may only become visible after testing. This screenshot illustrates the React loop in practice. Notice the alternating structure. Reasoning leads to an action, and the observation feeds the next step. This figure is a concrete example of the React framework at work. It shows how an agent can use intermediate reasoning to make a multi-step answer more reliable. Reflection takes the same basic idea and makes it more modular. One part judges the outcome, another part explains the failure, and then the agent updates its trajectory for the next attempt. Reflection is often easier to implement than a perfect planner, and it can improve performance a lot. The trade-off is extra latency and cost, because every thought, observation, and example consumes tokens. This figure shows how reflection rewrites the loop with explicit evaluation and self-reflection. The important thing to notice is the repeated correction cycle after each attempt. This figure highlights the reflection workflow. The model does not just act, it also critiques the result and uses that critique to try again more intelligently. With planning and reflection in place, the final question is which tools to give the agent. Tool selection is one of the most important design decisions in any agent system. The right tools depend on both the environment and the task, but also on the model that will use them. A tool set that works well for one model may be awkward or too large for another. There is no universal best tool set. Research systems range from a handful of tools to hundreds or even thousands of APIs, which shows how different the design space can be. Adding tools increases capability, but it also increases cognitive load for the model. More tools mean more descriptions, more choices, and a bigger chance that the relevant information will not fit in context. Because of that trade-off, tool selection is usually an empirical process. You test different inventories, measure performance, and revise the tool set based on where the agent succeeds or fails. A good workflow is to compare, remove, and refine. A straightforward starting point is to compare the agent with multiple tool inventories. That tells you whether a tool is helping in practice, not just in theory. Then test what happens when you remove one tool at a time. An ablation study helps identify redundant tools. If removing a tool does not hurt performance, that tool probably does not need to be in the inventory. Finally, watch for tools that the model keeps misusing. You should also watch for tools the model consistently struggles with. If prompting and fine-tuning still do not help, the better answer may be to simplify or redesign the tool itself. Usage frequency gives you one more signal. Another useful diagnostic is to plot tool call frequency. That shows which tools are central to the task and which ones are barely used. so you can refine the inventory intelligently. This graph compares how different models use different tools. Look for uneven usage patterns because they often reveal both model preferences and task-specific needs. This figure is useful because it shows that tool use is not uniform across models. Different models naturally gravitate toward different tools, even on similar tasks. The experiment supports two simple conclusions. Tasks differ in what they need, and models differ in how they choose tools. Both facts matter when you design an agent system. First, different tasks require different tools. Science QA leans heavily on retrieval, while TabMWP needs a different mix of capabilities. That means tool design should follow the task, not the other way around. Second, different models make different tool choices. The model choice matters too. Some models prefer a broader tool set, while others favor certain modalities more strongly, such as image captioning or knowledge retrieval. When you evaluate a framework, look at both the planner and the tools it supports. A framework is only useful if it matches the kinds of tasks and APIs you need today and can grow with you later. Different agent frameworks tend to focus on different ecosystems. That means the best framework for your project depends a lot on whether you need consumer web APIs, enterprise APIs, or something else. It is also worth asking how easily the framework can grow. Tool needs change over time, so extensibility is a practical requirement, not a luxury. A deeper question is whether agents can build better tools from simpler ones. That moves us from tool use to tool creation, which is an important frontier for future agent systems. Tool transition asks which tool tends to follow another. If two tools are often used together, they may be good candidates for combination into a more powerful composite tool. This diagram shows how tools can lead to other tools over time. The key insight is that repeated transitions can reveal structure that is useful for building larger skills. This figure visualizes the idea of tool transitions as a tree. It suggests that tool use can be analyzed and then turned into more powerful tool combinations. Voyager adds a skill manager that remembers newly learned skills for later use. The important idea is reuse. Once a skill helps solve one task, it can be stored and retrieved again for future tasks. To close this section, remember that agent success depends on two things: good planning and the right tools. If either one fails, the agent can fail, which is why the next topic is failure modes and evaluation. In this section, we look at how agent systems fail and how to measure those failures. The key idea is that evaluation is not just about whether the agent succeeds, but about understanding where and why it breaks. As tasks get more complex, there are more places for an agent to go wrong. Besides the usual AI failures, agents add new risks from planning, tool use, and speed, and some of those are much harder to notice than others. A good evaluation starts by naming the failure modes first. Then you measure how often each one appears, instead of collapsing everything into a single success score. There are simple benchmarks for studying these issues, including examples on the book's repository and several public leaderboards. The important point is that you can compare agents systematically, not just by anecdotal examples. Let's start with planning. Planning failures are especially common because the agent has to choose actions before it has actually executed them, and that creates several distinct ways to fail. The most common planning problem is tool use failure. That means the agent generates a plan that looks plausible, but the tools or arguments in that plan are wrong. The simplest case is calling a tool that does not exist. The agent may sound confident, but if the tool is not in the inventory, the plan cannot be executed. Here the agent asks for Bing_search, even though that tool is unavailable. This is a clear planning error because the issue is not the task itself, but the mismatch between the plan and the tools the agent actually has. A subtler failure is using a real tool with the wrong kind of arguments. In other words, the agent picked a valid action, but it failed to match the tool's required interface. In this example, the tool exists, but the agent passes two parameters when only one is allowed. That kind of mistake is easy to overlook unless you check the tool's signature carefully. Even when the tool and argument count are correct, the actual values can still be wrong. So evaluation has to separate syntax-level validity from semantic correctness. Here the agent uses the right tool with the right shape of input, but the number itself is incorrect. That means the plan is structurally valid, yet still fails to solve the task properly. Another planning failure is missing the goal entirely or violating its constraints. An agent can produce a reasonable-looking answer and still fail because it did not satisfy the actual requirement. Time is an easy constraint to forget in evaluation. A result that arrives after the deadline may be technically correct, but is no longer useful to the user. Reflection failures happen when the agent believes it succeeded even though it did not. This is especially dangerous because the system may stop searching or correcting itself too early. To measure planning quality, give the agent a task and a tool inventory, then sample several plans for each case. That lets you score not just whether the agent can succeed, but how reliably it can produce a valid plan. First metric. This measures plan validity across all generated plans. It tells you how often the agent can produce something that is executable and well-formed. Second metric. This captures the effort needed to reach a usable plan. Lower is better because it means the agent reaches a valid solution more quickly and consistently. Third metric. Now we move from whole plans to individual tool calls. This tells you whether the agent is using tools correctly once it decides to act. Fourth metric. This isolates the error of choosing a tool that should never have been used. A high rate here usually points to poor tool awareness or weak planning. Fifth metric. This checks whether the agent selects the right tool, but fills it in incorrectly. It is a good test of interface understanding. Sixth metric. This measures more subtle mistakes, where the tool is valid and the parameter list is valid, but the chosen values are wrong. That separates mechanical use from actual task understanding. Once you collect these metrics, analyze where the agent struggles most. If a tool or task type is especially weak, you can often improve performance with better prompts, more examples, or fine-tuning. If that still fails, the tool itself may be the problem. Next is tool failure. Here the agent chooses the right tool, but the tool output itself is wrong. So the problem moves from planning into execution or downstream translation. Sometimes the tool simply returns a bad result. A captioner might describe an image incorrectly, or a query generator might produce the wrong sequel, even though the agent selected the correct component. If the agent works in high-level actions and a separate module converts those actions into commands, that translation step can fail too. In that case, the plan may be fine, but the executable command is not. Sometimes the tool set is incomplete for the task. If the agent needs current internet data but has no internet access, then no amount of planning will fully solve the problem. Tool evaluation should be done one tool at a time, with every call and output printed for inspection. If you have a translator layer, benchmark that layer separately so you know where the failure actually comes from. To detect missing tools, you need to know what an expert would normally use. If the agent keeps failing in one domain, compare its toolbox with a human expert's workflow and look for gaps. Even when an agent succeeds, it may still be inefficient. So the next question is not just whether it solved the task, but how much work, time, and cost it used to get there. Efficiency evaluation looks at the resources consumed during task completion. That includes steps, cost, and the time taken by individual actions. First metric. This tells you how many actions the agent typically needs to finish a task. Fewer steps usually means a simpler and more efficient workflow. Second metric. Cost matters when each action consumes tokens, API calls, or external resources. A good agent should do the job without spending more than necessary. Third metric. This shows whether certain actions are slow or expensive. Some bottlenecks come from a single step, so it helps to identify the specific operations that dominate runtime. You can compare these numbers against another agent or against a human operator, but the comparison has to be fair. Humans and AI use tools very differently, so what looks efficient for one may not be efficient for the other. That finishes our look at RAG and agents, especially when the information needed exceeds the model's context window. Next, we'll move on to memory systems, which help extend what the model can work with. In this section, we'll build a practical model of memory for AI systems. The key idea is that different kinds of information belong in different memory layers, depending on how often you need them and how long they should last. Memory lets a model retain information and use it later. That matters especially in RAG, where retrieved context grows over time, and in agents, which need to remember instructions, plans, tool outputs, and reflections. A useful way to think about model memory is to split it into three main mechanisms. Each one serves a different role in how the system stores and uses information. First is internal knowledge, what the model has learned during training. This is built into the model itself, so it is available every time you query it unless the model is updated. This kind of memory is stable and shared across all queries. If you want to change it, you have to retrain or fine-tune the model because ordinary conversations do not alter it. Next is short-term memory, which comes from the current context window. It holds what matters right now, but it is temporary and limited in size. Previous messages can be placed in a context so the model can respond coherently. This is fast and useful for the current task, but it does not persist across separate sessions. The third mechanism is long-term memory, usually backed by external storage. It gives the model access to information across tasks, which is why it is so useful in RAG and agent systems. Unlike internal knowledge, long-term memory can be updated or deleted without changing the model itself. That makes it flexible when information changes over time. A good analogy is human memory. Some facts are built in, some are held in your immediate attention, and some live outside your head in notes, books, and computers. So the storage choice depends on how often the information is needed. Core facts belong in the model, rare facts belong in external memory, and task-specific details belong in short-term context. This diagram shows the hierarchy clearly. Internal knowledge at the core, short-term memory for the active task, and long-term memory for information that must persist. Notice how the three layers support different access patterns. This figure ties the idea together. It shows that an agent does not rely on one single store of information. It uses a layered memory structure instead. As AI systems got more capable, developers saw that memory was not optional. It became a practical requirement. External memory tools and provider support make it much easier to build systems that remember over time. The first benefit is managing overflow within a session. When an agent gathers too much information, memory lets you move the excess somewhere else instead of losing it. This matters because a task can easily generate more context than the model can hold at once. Long-term memory gives you a place to put that extra information safely. The second benefit is persistence. If the system remembers past interactions, it can stay useful even after the current session ends. That is what makes assistance feel personal instead of repetitive. If a system remembers your preferences, it can give better recommendations and avoid forcing you to repeat yourself. The third benefit is consistency. When a model can refer back to earlier judgments, its later answers are more likely to stay aligned with its previous ones. This is especially helpful for subjective tasks. If the model remembers how it answered before, it can calibrate its next response instead of drifting. The fourth benefit is structural integrity. Some information is better stored as structured data, and memory can preserve that structure more reliably than free-form text alone. This is useful when the agent needs to manage tables, queues, or other organized data. Instead of hoping the model reconstructs the structure from text, you store it in a form that stays explicit. A memory system usually does two jobs. It decides what to store, and it decides how to get information back when the task needs it. The first part is storage policy. The second part is lookup. Together, they determine whether memory is actually useful in practice. Memory management is the policy layer. It controls what should stay in short-term memory and what should be promoted or moved into long-term storage. This separation is important because not every piece of information deserves the same treatment. Good systems make that choice explicitly. Memory retrieval is the lookup step. It pulls back the information that is relevant to the current task from long-term storage. Here we focus on memory management, especially the add and delete operations. Long-term memory is usually cheap to expand, but short-term memory is constrained by context length, so it needs a clear policy. A practical design is to reserve part of the context for retrieved long-term memories. Whatever remains is available for short-term information, and any overflow can be pushed out into external storage. This is not a new problem in computing. AI memory management is really an instance of a broader systems challenge: how to use limited memory efficiently. The simplest policy is FIFO, first in, first out. It is easy to implement, but it can delete early messages that actually contain the most important instructions or goals. A smarter approach is to remove redundancy. If repeated information can be compressed or merged, you save space without losing much meaning. One common strategy is summarization. More advanced methods compare the summary with the original memory and keep the pieces that the summary missed, so the new memory stays compact but still complete. Another strategy is reflection. After each action, the agent pauses to evaluate what it learned and decides whether that information should be stored, merged, or used to replace outdated memory. First, the agent reflects on what just happened and extracts the useful takeaway. The first step is to inspect what just happened and extract the useful takeaway. This turns raw experience into a candidate memory. Second, it decides how that new information should interact with what is already stored. Then the system decides how that memory should interact with what is already stored. If the new fact conflicts with old information, it may replace it, merge with it, or be kept alongside it, depending on the use case. Contradictions are not always bad. Sometimes the newest information is best, and sometimes multiple perspectives are useful, so the right policy depends on the application. Let's wrap up the chapter by connecting the two big ideas: Retrieval-Augmented Generation, or RAG, and agents. This summary will show how they solve context limits, why tools matter, and where memory and safety fit in. It's no surprise that readers were especially excited about this chapter. RAG and agents are two of the most practical patterns in modern AI, so they naturally attract a lot of attention. RAG came first in the chapter because it solves a very common problem. Models often need more background knowledge than fits in context. By retrieving relevant information first, systems like copilots and research assistants can answer better, use information more efficiently, and reduce cost. The core RAG loop is simple. Find the right information, then use it to produce the answer. The retriever is the critical piece here, and lighter keyword methods like BM25 are strong baselines, while embedding-based retrievers are heavier but can be more powerful. Embedding retrieval depends on vector search, which is the same basic technology behind many search and recommendation systems. That's why techniques from those domains transfer so well to RAG. You can think of RAG as a limited form of agent. The retriever is just one tool the model can call. Agents go further by letting the model plan, reflect, and use memory to solve multi-step tasks in an environment with multiple tools. Adding tools makes a model more capable, but it also raises the cost of mistakes. Once an agent can act in the real world, security and defensive design become essential, because failures can have serious consequences. RAG and agents both work with more information than a model can hold in its context window. That's why a memory system becomes important. It helps organize, store, and reuse information over time. One final distinction is that both RAG and agents work through prompts and inputs. They do not change the model itself. The next chapter moves beyond prompting and shows what becomes possible when you modify the model directly. This note gives historical context. Before transformers dominated NLP, LSTMs were the standard recurrent architecture. It helps explain how quickly the field shifted once new model designs appeared. This reference points to early evidence that retrieval can dramatically improve factual question answering. The key idea is the same one behind RAG. Give a model access to relevant external information. This is simply an acknowledgement of an example used in the chapter. It's a small note, but it shows where a helpful idea or illustration came from. The point here is a practical one. Applications often expand until they hit the model's context ceiling. That's why context management becomes a design problem, not just a model problem. Retrieval is not a new idea at all. Long before modern LLMs, people were already building systems to search large document collections, and today's RAG systems build on that long tradition. BM25 remains one of the most important classic retrieval methods. Even with modern embeddings, it is still useful to understand and often serves as a strong baseline. This quote captures an important reality. Improving on standard keyword search is harder than many people expect. It's a good reminder to evaluate retrieval systems carefully before assuming newer methods are better. A retrieval pipeline often looks a lot like a recommender system. In both cases, the system is selecting the most relevant items from a large collection under practical constraints. Some teams find that organizing content as questions and answers improves retrieval quality. That makes sense because it aligns the stored information with the way the system is likely to search for it. This definition is the classic one. An agent perceives its environment and acts on it through available tools. That simple idea is the foundation for everything more advanced in agentic systems. This is a common complaint from the early days of agents. They could burn through API calls without producing enough value. It's a useful warning that autonomy needs discipline and control. Once a workflow gets complicated enough, it often gets split into multiple cooperating parts. That is why many real agent systems end up being multi-agent systems. This note highlights a useful framing. Sometimes the model is acting as a program generator. In other words, it translates a goal into a sequence of executable steps. This comparison links agent design to reinforcement learning. One part proposes actions, while another evaluates them, which is a helpful way to think about structured decision-making. There's a small contrast here with human conversation. Sometimes the early small talk does shape what comes next. The broader point is that context management matters in both human and machine interaction. This closes on a technical challenge for memory systems. It is difficult to know when a piece of information is actually being used. Without that signal, Usage-based cleanup strategies become much harder to design.